Hey, welcome back, everyone. I see we're a couple of minutes behind, but not too bad. Hope you had a good lunch. So in this afternoon session, we're going to hear from Dr. Jennifer Bob and Dr. Vishal Midja about some additional specific techniques for looking at exposure mixtures. Before I introduce Dr. Bob, I want to mention that next year's ISEE will be here in Atlanta, I think something like the 16th to 17th. And we hope you all join us. And we do plan to have, perhaps just before that, another workshop on methods, epi methods in environmental epidemiology. Yeah. So, we're very pleased to have Dr. Jennifer Bob talk to us about Bayesian kernel machine regression. She is an associate investigator in the biostatistics division at Kaiser Permanente. She's motivated by real-world studies and developed statistical methods for complex data sets, including spatial, temporal, environmental health data sets, and electronic health record data. Before joining Kaiser, she completed her PhD in biostat at the Johns Hopkins Bloomberg School of Public Health, and then had a postdoc at Harvard. She currently serves as associate editor of the journal Biostatistics and is the 2024 chair of the biometrics section of the American Statistical Association. I also want to point out that she developed a lot of the methods that she's going to talk about with kernel, Bayesian machine regression. So Dr. Bob, welcome and thank you.
Great. So it's a pleasure to be here. Thank you for the invitation. I'm looking forward to the discussion later to learn better about how these methods may be able to be adapted or refined to address some of the real world questions that folks are thinking about here at CBC. And I also was just reflecting and putting these together that it's been about 10 years since the initial Bayesian kernel machine regression paper. And so it's been exciting to see sort of the methods being uptaken by the community in terms of the software and the use of the methods. So I first wanted to acknowledge the co-authors on the different methods papers, including Brent Cole, who was my postdoc advisor at Harvard and was really spearheading. There's this new kernel machine methods. They might be interesting if used for environmental health applications. Shelley Liu at Mount Sinai, who's worked on the longitudinal extensions. Linda Valeri at Columbia, who's worked on a mediation analysis setting together with Katrina Devick, and Birgit Klaus-Henn at Boston University, who has really been key in thinking about the environmental health applications and how the methods might be useful in those settings. And I also wanted to acknowledge other collaborators, Chris Stewart, who helped with working on the R package, as well as environmental health colleagues at Harvard and Mount Sinai, as well as with the Superfund and Clean Air Center, and acknowledging the funding. So I'll first give some background, including a couple of motivating examples of settings where we wanted to look at complex mixtures and the challenges of those settings and how those motivated new methods. I'll talk about a default or standard method of doing a component-based regression. And then I'll introduce our Bayesian kernel machine regression or BKMR approach. And I'll spend a little bit of time talking about the approach in the simplest setting where you have a mixture at a single time point and an outcome at a single follow-up time point in this cross-sectional setting. I'll talk a bit about the R package implementation and give some usage examples of how to bring in the code and actually fit the model, and then highlight some of the practical considerations when you're fitting the model and how do you deal with convergence and things like that. And then I'll just briefly touch on some of those longitudinal mediation analysis settings, followed by a discussion. So our first motivating data set is a Bangladesh prenatal exposure study. And so the study is looking at exposure to arsenic, manganese, and lead. And the outcome was a motor composite score, which is a measure of neurodevelopment. And so at the time of the study, it had been known that individual metals were associated with neurodevelopmental decrements, but little had been known about the effect of mixtures. So the goal of the study was to estimate how prenatal exposure to metals affects cognitive development. And one of the challenges of the study is that it had been reported that there were some nonlinear effects of some of these metals, as well as possible interactions. So we wanted to be able to have a method that can account for those complex exposure-response relationships. Our second motivating study was the Boston air pollution study. So for this study, it was a toxicological study in which 13 dogs were repeatedly exposed for 5 hours, either to concentrated air particles, referred to as CAPs, or to filtered air in a crossover protocol. And it had been shown that the overall CAPS exposure was associated with elevated heart rates. So the follow-up goal was, if there's an overall effect of CAPS, is there individual constituents of the CAPS exposure that can explain that previously observed overall effect? So wanting to look at maybe bad actors using the terminology from before. But a particular challenge in the setting is the high correlation among the CAPS constituents. So you can see here, this is showing a correlation plot of the 13 the 13 CAPS constituents. And here we can see notably that aluminum and silicon have high correlation of 0.87, as well as sort of a cluster of highly correlated exposures. And then vanadium and nickel have a correlation of 0.8. So we want to be able to see, are there bad actors, but also know that we might not be able to disentangle effects if some exposures are really highly correlated. So as we learned a lot from Marianthi's presentation, which was really helpful context, there can be many different objectives of a multi-pollutant health analysis. So some of those that we've talked about have been detecting or estimating an overall effect of the mixture, identifying pollutants responsible for observed mixture effects, and we might also want to detect interactions among individual pollutants. And so we need statistical methods that can capture relatively complex exposure-response relationships that might include nonlinearity as well as interactions. And we may also wish to incorporate external knowledge, if we do have external knowledge, on the mixtures of interest from multiple disciplines. So really working collaboratively, if there's scientific knowledge, can we build that in? So this is probably like a straw man method, this standard approach. I don't think Marianthi even mentioned it, but at the time, this was sort of like, okay, we have multiple exposures, let's throw them into a component-based regression model. So there's only going to be a few equations here, but this is sort of our base equation where we have our health outcome yi for person I. And then we have a set of exposure variables here given by Z1 through Zm. And then we might have covariates, such as age, sex, that we might want to adjust for. So we put those potential confounders or prognostic variables in our X vector. And then we have a residual error term. So there's a few limitations of the sort of standard approach. It assumes that the components have an additive effect on the health outcome. It assumes that there's a linear exposure response function. Now we could generalize that. So we could, instead of including just Z1 through Zn, we could also include quadratic terms. We might want to allow for even other shapes of the nonlinear relationship. Marianthi also talked about, we might want to include interactions, but if we include sort of some pre-specified pairwise interactions, what about the higher order interactions? So once we start throwing in lots of interactions, we start throwing in nonlinear effects and allowing those nonlinear effects to have interactions. If we apply a standard sort of spline-based model with interactions, we can quickly lead to an ill-posed problem where we have a larger number of predictors as compared to our number of observations. And then we can have problems with fitting those models. So there's sort of a challenge in applying this if we want to allow more flexibility. And then there's also a potential for multi-collinearity. If we put multiple exposures in there that are highly correlated, we can have that reversal paradox that Chris talked about, where because they're highly correlated, it may look like one is having a negative effect, but it's really because they're competing to try to explain that variation in the data. And then if we're wanting to look at bad actors, we might want to do a variable selection approach. But sort of traditional variable selection approaches often presuppose this basic linear and additive form. And so we want to be able to extend that and move beyond those simple assumptions. So that sort of motivated this BKMR, Bayesian kernel machine regression approach. So this equation shouldn't look too much different from the one from the prior slide. All it's doing is it's replacing the linear and additive form of the mixture component Z1 through Zm with this H function, this exposure response function. So I'll walk through the different pieces of BKMR at a high level. So it first has this kernel machine regression. So what does that mean? So I talked about the challenges if we use basis functions like splines or quadratics with all the interactions leading to a large number of parameters in our model. There's an alternate way to write this exposure response function mathematically, and that's using a kernel function. And so for the kernel machine regression part is we're representing this unknown exposure response function H using the kernel function. So there's a couple features of using this kernel function approach. One is it allows for a parsimonious representation of a high dimensional exposure response function H. And there's also work that showed that once you have this kernel machine representation, you can express it in terms of a mixed model representation. So if you take the mixed model representation, you can then fit it using standard software for mixed models in the simpler approach where you don't incorporate variable selection. The other piece of BKMR is that we might also want to simultaneously do variable selection to identify which of the components, so which of these Z1 through Zm are actually important. Maybe some of them should come out of that H function and shouldn't be in there. So we want to quantify evidence for inclusion of each of our mixture components in that H function. See, should that component be in that function? And then the last piece is that we incorporate a Bayesian paradigm for inference. And one of the features that it fully accounts for uncertainty due to component selection. So instead of like a standard approach where you'd first do variable selection and then you refit the model a second time to get your standard errors, this approach allows you to do that all together. And so that can fully account for the uncertainty due to the variable selection process. Another opportunity with using Bayesian inference is that we can formally incorporate exposure complication as well as structure among exposures through prior distributions. So for those who may not be familiar with Bayesian inference, what you do is you specify a model and then you have a lot of parameters in the model, and then you might be able to have prior information about those parameters. You can say that you can express that prior information using a distribution, which is referred to as a prior distribution. And then you have your model, your likelihood, and then you put those together and you get a posterior distribution that's saying, given the model, given the data and the prior distributions, this is my updated information about what the evidence is regarding these parameters. Talk a little bit about more practically how that works in a few slides. So going back to the variable selection piece, so we want to be able to identify which of the mixture components should really be included in our H function. And so we're really just looking at this one at a time, but it actually is happening all together in the model fitting. But we're asking, is Z1 an important mixture component? Yes or no? Should that be included in the H1? Is Z2 an important mixture component? And it's doing that while saying, should it be included in the mixture component in the exposure response function, potentially allowing for nonlinear relationships. So if you wanted to do that parallel test where you had the basis function representation, you'd have to test whether several of the different parameters are not zero. So you'd have potentially a high dimensional test to look at each exposure. In the kernel machine representation, testing for whether the variable should be included in the model is just saying, looking at just one single variable for each component, even with this complex relationship. So how it works is we augment the kernel function with a non-negative parameter R1 through Rm. So each mixture component Zm has a corresponding auxiliary parameter Rm. And these auxiliary parameters are such that if Rm is equal to 0, that implies that the mixture component M is no longer included in that exposure response function. And so practically what we are doing is we estimate the posterior inclusion probability. So again, I talked about posterior distributions, but that's the posterior probability that this Rm parameter is greater than 0. Given our data. And so this ends up being a value between 0 and 1, where a posterior inclusion probability of 1 is saying that there's very high probability that this should be included in the model, and a value of 0 is saying that there's no probability this should not be included in the model. But you can have a different amount of evidence depending on what these posterior inclusion probabilities are from 0 to 1. So I talked about the multicollinearity issue and looking at the Boston air pollution example. We might also wish to sort of reflect some structure in these exposures. So we also developed a hierarchical variable selection approach where we would partition the exposures into mutually exclusive groups. So for example, these highly correlated groups could be a group S1. This other set of highly correlated exposures could be group S2. And then you can also have exposures that are just in a group by themselves if they're not highly correlated with others. And so then conceptually what this approach is doing is it's looking at each group and saying, should this group Z1 through Z3 in this little schematic here be included in the model? And if so, is it Z1 or Z2 or Z3 that's really reflecting the association of that group? So in our Bayesian framework, what we estimate in order to get these two pieces is we estimate a posterior inclusion probability for each group. And then we estimate conditional posterior inclusion probabilities for each mixture component within the group, given that the group was selected into the model. And I'll illustrate that in a slide or two with the Boston air pollution example. Okay, but first going back to our Bangladesh prenatal exposure study, this is showing some of the results that you can get from applying BKMR. So for this application, we were estimating the association between manganese, arsenic, and lead. And so this slide is showing different plots of our exposure response function H of these three metal exposures with the motor composite score. And so what this top left plot is showing is the relationship of manganese and arsenic with the outcome at median levels of lead. And so areas of this region that are red are showing exposure values where you're having higher a neurodevelopment score, and then the bluer shading is showing where you're having a lower neurodevelopment score. This plot on the right is showing the observed location of our data points, and it's showing the posterior standard deviation, which is a measure of how uncertain the estimates are. So places that are blue are showing lower posterior standard deviation, so that indicates greater precision. So we really are estimating that exposure response function more precisely where we have more data. And then areas that are red are places where we may only have 1 or 2 people exposed at those levels, and so we have a lot of uncertainty of our exposure response function in that location. And I didn't even shade some of the places where we don't have data, because we want to be careful about extrapolating where we don't have data to say that the model will tell you what it thinks the exposure response function would be, but there's no data to support that. And so we wanted to be careful about over-interpreting when we don't have data. And so what these results indicated to us was that there appeared to be evidence of nonlinear effects and interactions. So to make that a little bit easier to see, I've taken this heat map here and split it out, where it's showing the relationship of manganese with our motor composite score at the 10th, 50th, and 90th percentile of arsenic levels. And what we observed was that there appeared to be this inverted U-shaped relationship of manganese with the motor composite score, and it appeared to be present at middle levels of arsenic and not at the other levels. And so initially when we saw this inverted U-shaped relationship, it seemed we weren't quite sure about whether this was plausible. In returning to our scientific collaborators, they indicated that manganese was a nutrient in lower levels. We might expect that it would, so for example, if we go from the lowest levels of manganese, if you increase a bit, it increases the motor composite score up to some point. So it is helpful up to some point, after which further increases in manganese is then associated with lower motor composite score. So it may be neurotoxic after a certain point. Now that may be over-interpreting these findings. I wanted to mention that this was just a subset of the initial data, and the final analysis was reported in a subsequent Valeri publication where we didn't see these trends. But this was a great case study to illustrate that you can observe these nonlinear effects and interactions using these methods. This is highlighting results for the Boston air pollution study, focusing on the variable selection. And this first plot is showing the posterior inclusion probabilities when we implemented the component-wise variable selection. So again, recall here that we have 13 exposures, some of which are highly correlated with each other. The y-axis is indicating the posterior inclusion probability. So again, 0 is that it should not be included in the model. 1 is that it should always be included in the model in the exposure response function. And when we look at this, nothing's really jumping out. We're seeing all the posterior inclusion probabilities are below 0.4. And so, it's not really seeming to suggest that there's a really large effect of any of the individual CAPS constituents. But this is where the hierarchical approach can really enable us to potentially account for some of these correlations. And so when we grouped some of the highly correlated exposures together, we got a group-wise posterior inclusion probability of close to 0.8. So suggesting more evidence that there's potentially a bad actor within that group. And then the group including nickel and vanadium. So these were another sort of group of correlated exposures, had a group-wise posterior inclusion probability of about 0.3. So it suggests that a bad actor might be likely within group 1. And then looking here on the right is the conditional posterior inclusion probabilities for those constituents within group 1, given that group 1 is in the model. And we're kind of seeing something a little bit similar to that first plot. There's nothing that's really jumping out. It might be that silicon or manganese could potentially be one of the driving exposures, leading to the impact of that group on the outcome. Okay, so I talked a little bit about the motivating data sets and showing some results to illustrate some of the advantages of using these methods. I wanted to touch on the R package if you're interested in applying the methods. It's just called BKMR, all lowercase. And it allows for a flexible model specification. So you can do no variable selection or either the component-wise or hierarchical approach. It also has the flexibility where if you have clustered outcome data, so for example, if you have individuals who are clustered within families, you can include a random intercept to account for a correlation within a cluster. I've also implemented a faster version using a Gaussian predictive process. So briefly what that does is if we go back to this prior plot here showing our exposure data, we have a lot of points of exposure around this area. We might not need to have, need to be able to predict the exposure response function at every single point in our observed data. So what the Gaussian predictive process approach does is that you put knots, you try to cover the space of your exposures with knot locations. And the idea is that you would have fewer knots than you have number of individuals. And so that will greatly reduce the model fitting time. So that's the Gaussian process, predictive process implementation. And it's also implemented for continuous outcomes as well as binary outcomes. And for binary outcomes, it uses a probit regression, which you may be more familiar with logistic regression. Within Bayesian model fitting, there's this really nice relationship between normally distributed outcomes and binary outcomes when you use a probit link. So it's just a natural way to implement within the Bayesian context. The package also has different post-processing functions. So once you fit your model, you might want to do graphical displays to look at your high-dimensional exposure response function, as well as to summarize numerically the model fit. And Marianthi in this morning's presentation showed some examples, and I'll walk through a few of those in more detail. And it's freely available for download. So if you have R on your computer, you can just install the package using the install.packages command. You can also get it from GitHub as well. So I'll just have a couple slides with code. I'm not going to go through all of the code, but these are all available either in the vignettes or in an environmental health paper that's highlighting the features of the R package. But to briefly go through this, so you would first load it. Once you've installed the R package, you can load it in. So you'd use the library command to load it in. The next line is generating an example data set. So there's a built-in function where you can simulate data. But you might have your real data set not needing to simulate, but to make this reproducible, I'm just simulating data for this usage example. And then the workhorse here is this KM Bayes function, kernel machine Bayes. This line is illustrating how you'd fit the model without variable selections. You would just tell it your outcome vector, your exposure matrix, and your covariate matrix. And to fit it with variable selection, you just say var cell equals true. You likely would want, the default number of iterations is fairly small, so you would likely want to have a higher number of iterations, and I'll talk a little bit about that in the practical considerations piece. And then this last bit of code is showing how you would generate the knot matrix for the Gaussian predictive process. So this 2 colons here is just indicating that we're using this cover design function from the fields R package. So you would need to have that fields R package installed to be able to run this line of code. But then once you have the knots that cover the exposure space, you just tell the KM Bayes function that you have this knot matrix, and it will go ahead and use the Gaussian predictive process approach. So I'll touch on some of the practical considerations, but a lot of these come from vignettes that are available online. So there's an R package overview guide. If you just Google it, it's one of the first links that comes up. And then in that software paper in environmental health, there's 2 reproducible examples, a continuous outcome that comes from a workshop that the National Institute of Environmental Health Sciences held several years ago that used 2 data examples, including one from Chris. But this simulated data one, we have code that implements the methods for that data set. And then there's also a binary outcome example with a simulated data set. So for some practical considerations when you're using the software, so when you specify the covariate matrix X, each column is a covariate. So for example, age or sex. You could add a quadratic term. For example, you would just have age squared would just be another column in your matrix. If you do have a categorical covariate, you would code that up as different dummy variables. So if you had a categorical variable with p levels, you would create p-1 dummy variables for the non-reference group categories. And if you need help with that, feel free to email me and I can give you kind of example code for how to do that. For specifying the exposure matrix Z, again, each column is an exposure variable, so a pollutant or one of your mixture components. And I wanted to note this because I've gotten some questions about it. Right now, we just have it for continuous exposure. So if you wanted to look at interaction between some continuous variables and then some categorical variables, unless the categorical variables have many categories that you could model it effectively as continuously, it wouldn't work with the smaller number of categories or binary with the way that it's currently implemented. It's also helpful to have the exposures be on a similar scale. So that's means having a similar range of values. Because if one has a much larger range of values than the other, then there's sort of more variability in that measure, and that could lead to complexities when you're fitting the model. It's still possible to do that, but you need to think through more about the prior distributions on the RM smoothing parameters. So it's just much easier to have them all kind of be on the same scale, and you can do that by standardizing the exposures. I also want to touch on a little bit if you have really skewed exposures. You've seen lots of log transformed variables. That's probably a good idea because if you do have a lot of skewed variables, you'll get a really wiggly exposure response function and very uncertain estimates if you don't have a lot of data in those parts of the exposure space. So those are just some practical things to keep in mind. I wanted to get a little bit under the hood with how model fitting works, because that'll be important if you're fitting the model for how do you assess the model if it's done converging. So just to touch on, it uses Markov chain Monte Carlo, which is a sampling approach where you're generating samples from the posterior distribution of the quantities of interest. So for example, posterior samples of our estimated exposure response function H at different values that we want to look at. Marianthi also talked about the importance of setting the seeds. You get the same result if you rerun it and maybe trying some different seeds. So there's just the set.seed command in R. And then how inference works for Bayesian inference, given your posterior samples, you can take the mean of those, and that's the posterior mean. So that's the mean given your data and your priors that's supported by, that's consistent with the data. And then you would also get the Bayesian analog for a 95% confidence interval as a 95% credible interval. So you would just take the 2.5th and 97.5th percentiles of the posterior samples to get, that's one type of way you can get a credible interval. It's important to assess convergence. So there's a simple approach where you can visually inspect trace plots, and I'll have on the next slide show you an example of that. But I wanted to call out there's also more options implemented in an add-on package. I didn't create the package, but it looks like a very nice one called BKMR Hat, which is implementing more sort of formal ways of assessing convergence diagnostics. And a great way to do that is that you actually run multiple different chains from different starting values. So that's getting at a little bit what Marianthi was talking about with variability of where you start from or with the seed. If you start it from different starting values, you assess convergence to see if the chains are ending up at the same place. And so that's really more evidence that you've converged versus if you just do a single chain. So I recommend looking into that option. So what do you do if the model hasn't converged? So you can either run it for a larger number of iterations, and you would use the iter argument, or you can change tuning parameter values. I won't go into too much details here, but just at a high level, some of the steps of the sampling algorithm is it generates a proposal value, and then it's either accepting or rejecting. So it's this acceptance, rejecting, Metropolis Hastings step. And it basically is around a random walk. So the new value that's proposed is based off of the current value. And you can change the variances of the proposal distribution so that you would either explore more of the space and you can tune it so that you get a good acceptance rate, which will give you better mixing. So that's another option, but it might be helpful to work with somebody who's had some experience with doing Bayesian model fitting. But here's an example of a trace plot. I've just found it from the web, just to give you an example of what a plot that would, where the parameter has converged. So the one on the top is showing what the trace plot would look like. So the x-axis is just showing what iteration you're on in your sampler, because you generate posterior samples. So what iteration you're on. And then the y-axis is showing the parameter value. So you're going to see some variability. There's some correlation over time because of the way that the proposal distribution works, but it looks like it's converged because it's kind of stable around a certain mean function. The second plot is showing what you might see at first when you're first starting the sampler. So it'll start to propose new values. It's not really converging here, but then it sort of reaches the target distribution and it starts to get good conversion. So if this happens, you would just not use the iterations for inference before it's converged. And the default setting in BKMR is that it uses the second half of the number of iterations. So if you fit it for 10,000 iterations, it would use the last 5,000 samples. But you're going to want to make sure that you've achieved convergence there, either using these visual diagnostics or with that BKMR R package. This example here is showing one where maybe it's converged, but they're so highly correlated, you're not going to get stable estimates. And so one approach is to fit this for just a larger number of iterations, or you could alter those tuning parameter values to try to get better mixing of the chain. So those are some ways that you can visually inspect the trace plots to see what's happening. And you'll want to do that especially for those RM parameters that control the smoothness of the exposure response function as a function of each of the pollutants. Okay. Oh, I think I already did this slide. Let's see. Okay. So another practical consideration, as I talked about prior distributions, they can encode prior knowledge if you have them, but more likely you might not want to encode prior knowledge. You might want to see, I just want the data to really tell me where there's support in the data for these parameter values. So the default settings in the R package include non-informative priors for the coefficients on our covariates and for the residual variance. But I do want to acknowledge that results can be sensitive to the prior distributions of those RM parameters. Recall that there's an RM for each pollutant M, and those control the smoothness of the exposure response function as a function of that exposure. And so, especially when you're conducting variable selection, you'll want to consider different priors. So the default is that it's an inverse uniform prior where there's a lower and upper bound. And in the Valeri et al. Application that uses the full Bangladesh exposure data, we considered alternate values that allowed for lower, higher degrees of smoothness relative to the default settings. So the general guidance here is to consider sensitivity analyses, especially for these parameters. For the posterior inclusion probabilities, when you're running BKMR with variable selection, I already mentioned this, but just to reiterate, the PIP or PIP is the posterior probability that exposure ZM is in the model, and it ranges from 0 where it's not included to 1 where it is included. But in practice, the values of these PIPs can be sensitive to the priors on the RM parameters. But we have seen that the relative ranking tends to be more stable when you change the parameter about the prior distributions. So our thinking has moved past beyond just looking at the PIP values for whether the measure should be included and focusing more on the magnitude of the estimated exposure response relationship as well as the relative ordering of the PIPs rather than on the PIP values themselves. So it's helpful to show them so you can see the relative ranking, but wouldn't interpret that directly as the probability that it should be included given that it can be sensitive. So given that there's the component-wise and the hierarchical variable selection, when should you use one versus the other? I tried to make this clear, but sometimes it might not always be clear, but the hierarchical approach does make a strong assumption that just one exposure from each of the pre-specified group contributes to the outcome. Now that could be generalized to not make that assumption, but how it's currently implemented is more of a practical approach to handle multicollinearity, since the data may not be able to distinguish between two or more highly correlated exposures, like we observed in the Boston air pollution study, even if both could contribute to the outcome. So going back to our Boston air pollution plot, I don't know if I want to go all the way back to it, but let's see if we can get there quickly. Right now, the model would say that just only one of these would be included in the model at a time. And we would say, maybe it's silicon or maybe it's manganese that's driving the effect. Well, maybe it's both. Maybe it's silicon and aluminum. Maybe they're both important. But because they're so highly correlated, we don't have enough variability in the data to estimate independent effects. So this is more of a practical assumption saying, given that we can't do this, we want to just let the data tell us which of these is important. So that's why we group them based off of just the highly correlated exposures. So let's see if I can get back. Okay, so how I've tended to view the choice between these two is that I prefer to use the component-wise selection, unless you would have prior knowledge that just one component contributes, which seems unlikely that you would really have that knowledge. That's why we're doing these analyses to begin with. Or if the correlation of exposures is too high that you wouldn't be able to disentangle the health effects. So practically what we've done for other applications when we have the highly correlated is we just pick one. This is avoiding that you need to just pick one to include in the model. You can include both, but you're just grouping them together, acknowledging that there's limited ability to disentangle their effects. Okay, so I talked about how once we fit the model, one of the goals is to visualize the exposure response function. And so the vignette that I pointed to will have code that can show you how to reproduce this plot. So this is a simplified example where there's this true H function where Z1 and Z2 have a nonlinear and interactive effect on the outcome, the simulated outcome, and Z3 and Z4 do not have an effect. So from the model, from one of the post-processing functions, you can easily plot the exposure response function of each exposure where all the others are set to their median value. So this is the exposure response function of Z1 with the outcome when Z2, Z3, and Z4 are at the median value. This is Z2 with the outcome when the others are at their median value, and so on. A variant of this plot that can start to give you some depiction of possible interactions is that you can look at the exposure response function of one of the exposures where that second exposure is set to either the 25th, 50th, or 75th percentile, and the other exposures are fixed. So just from looking at this, we can see that it looks like the exposure response function of Z1 varies depending on the value of Z2, suggesting interactions. So beyond getting a visual plots of the exposure response function H, you can also obtain numerical summaries from BKMR. And so this code is illustrating it from our continuous outcome example. And Marianthi already showed some plots illustrating some of these exposure effects. So we can estimate overall effects. And so what we do is we're estimating the adjusted mean difference in the outcome, comparing when all of the exposures are at a high level versus when all the exposures are at a low level. And you can vary what you mean by high and what you mean by low. So to implement that, you would specify what the model fit is. So fit KM, the exposure, outcome, and covariant matrix. And then you would specify a sequence of values that's considered sort of the high level, the comparator level, and then you would have a fixed level where you'd want to compare them at. But you can specify these to be whatever you want. I think these might be the default settings. And then just note here that using an exact method, there's different ways of getting at these risk summaries. In addition to doing the overall effect of the mixture, you can estimate the single exposure effect. So that's the adjusted mean difference, comparing each exposure at a high versus a low level. So here we're comparing, for example, exposure 1 when it's at the 75th versus 25th percentile, where you fix all of the other exposures at different levels. And then that allows you to assess interaction. So I'll show you this on the next slide, but just wanted to give you a little bit of code here, which is all, like I said, in the vignette. So I talked about there's these different methods of getting out these numerical summaries given your model fit. I think the default setting is to use the approx method, which is just the fastest. And so our general guidance is that when estimating the exposure response function H, the exact method is preferable, but it does take longer to run depending on the size of your data set. So I'd suggest that if you're able to, if it's computationally feasible, that you would use the exact method for generating these numerical summaries. And there's more details on the differences between them in the vignette. So we've already seen some variants of these plots before. So taking that exposure response function that we had, we get estimates of the overall effect. So here the 50th percentile is the reference, and then we compare when all of the exposures are at these different quantiles compared to when all of the exposures are at their 50th percentile. These are showing plots of the single pollutant effect. So again, Z3 and Z4 had no association in the generated data, had no effect in our simulated data set. Z1 and Z2 did. And so this is suggesting potential interactions because we're seeing that the single exposure effect of Z2 changes when we vary the levels of the other exposures, and similar for Z1. You can also quantify interactive effects. So these are basically just taking these blue points minus the red points. So you can get the posterior mean and posterior 95%, or the 95% credible intervals for these. And in this data set, I know that there is interaction because I know the truth. And it's estimating interaction, but it has a really wide confidence and credible interval around the estimate. So you can estimate these interaction parameters. So I don't have a lot of time, but I have maybe a couple of slides for each of these extensions of BKMR. So we have extensions for the time varying exposure setting, longitudinal outcome setting, and then the setting of mediation analysis. So up until now, we've talked about single exposure time point and a single outcome time point, but pollutant mixtures at different time windows could have different effects. So for example, in the context of pregnancy cohorts, specific exposures might be more harmful to the developing fetus during different stages of pregnancy. And so the lagged kernel machine regression, LKMR approach, estimates the effects of the pollutant mixtures over multiple time points, and it enables you to identify critical time windows of susceptibility. So this equation is very similar to the original BKMR equation, except for we have a HT function for each time point. So we just have a separate effect of the mixture at each time point. And the hierarchical model formulation of LKMR with random effect distributions imposes shrinkage because we end up with even more parameters once we have mixture effects over time. And so it's shrinking across neighboring time points, and then it's shrinking within time points because certain time points may not be relevant if they're not part of the critical window. So an example illustrating this method is the ELEMENT study, which is a prospective birth cohort study of risk factors for neurodevelopment. And the exposures are measures of history of exposure to metals obtained from tooth dentin. And you can see this really cool image showing how they measure these metals from teeth. And the challenge is to account for the time varying exposures and the potential synergistic effects. We have mixtures and time varying effects. And this study had 2 time points of exposure prior to birth and then 2 time points after birth. There's just showing a single plot summarizing results. This is showing the estimated association between pre and postnatal exposure to metal mixtures and neurodevelopment at age 8. Where we're showing this cross-section of the exposure response function of manganese at low versus high levels of lead, where the other 4 metals are fixed to their median values. And just wanted to highlight here that there's potential evidence of interaction. So seeing different effects of manganese at low versus high lead, and also potential for different effects at different time intervals. So it seems to be that there's positive association potentially at the 3rd trimester, or a suggestion of a negative association at months 3 through 6. So you can have different potential effects over time. The Bayesian varying coefficient kernel machine regression is another generalization that allows you to estimate the effect of the mixture when you have longitudinal outcome trajectories. So for example, how do metal mixtures affect changes in neurodevelopment over time? And so rather than having just a single kernel function here, we have 2 kernel functions here. This H1 is the cross-sectional association between the mixture and the baseline outcome. And H2 is the association with the change in outcome over time. So you can see that it's a varying coefficient on age, because as children age, the effect could be different on their cognitive trajectories. And both of these are flexibly modeled with a kernel function. And then this is just a single slide, because Marianthi also talked a little bit about this BKMR for causal mediation analysis. But again, the idea is to decompose the total effect into a direct and indirect, that is mediated effect. And then in contrast to standard approaches, it allows for complex exposure mediator and exposure mediator response functions using kernel machine representations. And this is important for causal inference because we need correct specification of the model in order for association estimates to have causal interpretations. So just to wrap up, there's still limitations. Like we've learned, no method is good for all questions. BKMR allows you to visualize interactions. Even that can be challenging when you have high dimensional exposure response functions, but it's not testing for the presence of, is there any interaction between these two exposures? Another key challenge is that fitting flexible Bayesian models can be slow. There are faster versions, the Gaussian predictive process, but even with that, big applications with many observations can just not really be feasible, especially when you're saying to do sensitivity analyses. And there's also desire for additional models to be implemented. So to summarize, mixture health effect analyses often address a range of questions, as has been the theme of today. The benefits of BKMR is that it avoids additive and linear assumptions, identifies components responsible for health effects, and it allows you to summarize the shape of the exposure response function and look at different numerical summaries to quantify that relationship. The hierarchical variable selection can also account for highly correlated exposures. I didn't go into any of the simulation studies, but the papers illustrate some realistic data generating scenarios illustrating performance of the methods. And then we talked about extensions to a broader range of settings. So again, thank you. And I know we have a little bit of time now for the Q&A. Looking forward to the discussion later.
Well, thank you, Dr. Bond. That was really informative and helpful. So let me start off with a question that came in from someone online. Actually, the person asked a couple of questions. If you look to what extent the performance of BKMR degrades as more exposure variables are included, and is there an appropriate number of exposures above which variable selection or filtering have to be done before running BKMR?
Yeah, I was actually reflecting on that when that question was posed for one of the earlier methods, because I've had that kind of on my list of questions that I've gotten and questions that I would like to answer, but haven't had time or bandwidth. So if somebody would want to collaborate on that, I think that would be a really great work to understand where it would break down. Conceptually, it can work when you have more predictors, the number of observations given how the mixed model representation with the kernel machine. So like conceptually, yes, it seems like you can have a lot of exposures, but we know things tend to break in practice. So our simulations were based on our motivating Boston air pollution study with the 13 exposures. So I think it would be really valuable to have a better answer than I've just given. So I think that's an area that I would like to see more work be done on.
Okay, fair enough. Ray, you want?
Congratulations on a wonderful and important method. I think I was at JSM when you first presented this 8 or 9 years ago, but I have probably a million questions, but let me stick to two. First, assuming everything's gone fine, the model's converged, and you got results, and everyone's happy. It seems to me that, and as you've already pointed out, there are the non-linearities can be toxicologically difficult to justify. In other words, greater exposure to the pollutant in a mixture seems to be associated with improvements in the health outcome. Because the toxicology experiments don't really exist for those kinds of mixtures, I'm going to guess that whatever explanations you try to supply in a paper are probably going to be unsatisfactory generally. But I'm wondering what your experience has been with addressing those non-linearities, as a result that you have to maybe somehow explain or discuss in the manuscript. And my second question is small. I'm wondering, are you working on a book?
Oh, am I working on a book? No, to answer that one. But for the first question, in terms of you could observe things that might be against what your scientific knowledge would bring. I think there's always, I mean, these are often observational studies, even that toxicological, which did the crossover protocol, you're not randomizing the levels of the constituents. Some are exposed to filtered air, some are exposed to caps, but within caps it's observed. You're not controlling the levels. So I think as scientists, we can often like interpret things that may or may not be true. So I think that's why I would feel like I'd want to see things that maybe not expected or surprising to be reproduced in other data sets. You can't be in a randomized setting where you can do a controlled experiment to at least see multiple studies converging on similar findings. Because especially when you're looking at lots of different exposures, lots of different outcomes, lots of different summaries. I mean, we haven't talked too much about it, but you can have these multiple comparisons, right? So you're going to have something show up as significant. In principle, those posterior inclusion probabilities should not be subject to the multiple comparison. But again, with how I've ended up interpreting them, I don't feel like you can just use the values of those posterior inclusion probabilities. So I still think that figuring out what's a real association and what's not, I mean, having sort of some pre-specified outcomes, if you've seen an association, and then you can do another study and have that be a pre-specified hypothesis that you look at. And then if you see it, that's really supporting it. As well as potentially having standardized protocols of different studies so that multiple studies are looking at the same relationship versus like, you know, Marianthi said, you're not going to just show the method that showed the result you like. And so thinking about applying some standard toolbox methods to different data sets, which was one of the hopes of that NIEHS workshop that was comparing the different methods. But that's certainly a challenge when you have mixtures because you have a lot of exposures. And so you potentially, and with different exposures at different time points, you might sort of end up over-interpreting, you know, the couple of places where you had a significant association. So that's sort of the general challenge with these analyses.
Thank you. So there is one more question from somebody online. And it goes, the current formulation of BKMR allows for nonlinear associations between exposure and outcome, or exposures and outcome, but the covariates are still entering the model in a linear form. Have you thought about how you might address that? And I would think you could explore nonlinear forms for the covariates, even splines perhaps. But
yeah.
Then how would you assess?
So how I've tended to do it is for the covariate, I tend to want to specify a model that is fixing the covariate adjustment to like remove the effect. So if age might have a nonlinear effect, I would actually model it flexibly with splines if I have enough data points to be able to do that flexible modeling. So I would include the age maybe with splines with several degrees of freedom in there. And you don't have to, you can do that in that X function, but it would be with a spline basis representation or adding polynomial terms. So you can do that within the X function. Another idea is that you could include some covariates provided that they're continuous in your H. Sorry, they would be, the initial approach meant to say that they would be in the X matrix. You could put some covariates in your H functions. You could look at age as like a modifier, and then you could have some plots where you set age to different values. So you could put some covariates in the H function, but that would be more like exploring interactions. It feels like it would be more exploratory. But if you wanted to estimate the mixture effect and then make sure you're adjusting for confounders of that, I would adjust for confounders sort of in a standard way. Unless you have a large number of confounders, then you are going to need to do some type of confounder selection method. But confounder selection methods are different than mixture component selection because you want to make sure that you're selecting all the confounders, not just variables that are predictive of the outcome. They need to be predictive of the outcome and the exposure. So there's whole like areas of research on how do you do confounder selection. And so that would be an area where if you want to try to combine that with BKMR would be interesting future work, I think.
Very good. Well, thank you, Dr. Baum.
Thanks.
Appreciate a great presentation.